Hi everyone, my name is Shengpu Tang, and I'm here to tell you about our paper, Model Selection for Offline Reinforcement Learning, Practical Considerations for Healthcare Settings. Reinforcement learning is an increasingly popular technique that has great potential in healthcare. While supervised learning learns to predict outcomes, RL tells us what actions to take to get to that outcome. Recent work applied RL to learn optimal treatments for sepsis and many other problems, but this framework presents new challenges, and model selection is one of them. Model selection is the process of selecting a final model from many. In supervised learning, one typically selects the model with the best performance on the validation set, usually in terms of loss or accuracy. In RL, measuring validation performance requires an online setting, such as Atari games. However, in many healthcare tasks, this is not possible due to safety and ethical concerns. Thus, we must rely on offline techniques. Despite a growing literature of policy evaluation in recent years, they have not been systematically explored in the context of model selection. Thus, in this work, we investigate how OPE can be used to inform model selection in offline RL. We first review and compare popular OPE methods in terms of accuracy and computational costs. While some approaches offer greater accuracy, their additional dependencies contribute to increased computational requirements. To balance the trade-off between accuracy and efficiency, we propose a simple two-stage approach to accelerate model selection. Applied to a sepsis simulator, FitIQ evaluation provides the best estimates of validation performance, achieving the highest correlation with true performance and the lowest regret of the OPE methods we tested. In contrast, weighted importance sampling performed the worst. To measure computational cost, we looked at the number of auxiliary models required to evaluate 96 candidate policies. Weighted importance sampling is the most efficient, as it only requires one auxiliary model and applies it to all policies. FQE, on the other hand, requires retraining new models for each policy and each time horizon. For our sepsis problem, this requires nearly 2,000 additional models. This quickly becomes intractable with a large hyperparameter space. Given this accuracy versus efficiency trade-off, we proposed a two-stage approach to combine weighted importance sampling with FQE. In the first stage, we use weighted importance sampling, which is less accurate but more efficient, to print away low-quality policies. This saves computation in the second stage, where we apply FQE, which is less efficient but more accurate. In our experiments, we reduced computation by more than half compared to FQE while maintaining overall accuracy. To find out more, come visit our poster or read our paper, in which we also discuss many practical aspects of model selection in offline RL, including heuristics for setting auxiliary hyperparameters and common choices of auxiliary models. Our code is available online. We hope these practical learnings can guide researchers in healthcare to learn better treatment policies from real clinical data. Thank you.